Dr. Ma, it's a great model showing the falling friction coefficient. So the modeling showing this, and he also referenced to the literature of that is Siemens. We saw a lot of those reference to the falling friction that was generated from the locomotive test. Have you done some tests or experimental from either revenue service or from your rural rig showing similar falling friction coefficient in addition to what we already saw before, like the Siemens did?
Because I'm a young researcher, so I have not that resources. But we are trying to cooperate with other researchers in China, and they have the facilities. We want to test them with their experiment setup. Yeah.
Thank you.
Maybe you can give a comment on that?
Yes.
So your question was on falling friction on test rigs or general? Because we did a lot of testing with locomotives and other vehicles together with Siemens on test rings, and we always observed a lot of...
Yeah, other than locomotive, those tests like a regular vehicle or car, other than locomotive, have you done any of the tests?
You can also find some work in the literature for example, I think for passenger coaches and so, or not passenger coaches, for commuter trains. I think it's the phenomenon is very well known. Okay, I have two microphones. I think the main reason is the temperature with increasing temperature.
Double microphone.
Yeah, sorry.
Okay, so but let's start from the first presentation. So, are there any comments to the first presentation?
I think both of you asked how the contact patch affect my simulation result, right?
I was thinking about it. Each point in the contact patch, the material has got there by travelling through the patch.
Yes.
So to calculate what the final state of the material is, you need to have done a integral through the path.
Yes, that's right. Yeah. For each creepage, we simulate it over like 5 seconds, and because it will reach an equilibrium, and we average that equilibrium.
Okay.
So usually for these methods, the input to the model brings in the sliding velocities. So the model itself doesn't calculate that, but it uses as an input. At least you refer to the traditional tribology, so that's why I'm assuming. So please correct me if I'm wrong. But that's usually the input. It's not an output. So whatever his contact model was that he used will supply the localized.
If you want to update the velocity, you need the dynamic of the reel.
Right. Yeah.
Okay, and I have a question, or maybe comment. What is the ratio between or input of microscale and macroscale to the general curve
so
of
the geometry of the wheel.
interaction coefficient?
Yeah, the geometry of the wheel and the reel will provide the geometry of the contact patch.
Yes.
And within the contact patch, we sample about several hundreds of asperities. And the asperities have different sizes. They follow the Gaussian distribution.
Okay, but of course it must be, you use a stochastic model, yes?
Yeah,
distribution. No?
Yes.
So it must be a lot
of samples.
So contact is discrete.
Yes,
and a lot of
it's discrete. You can see the force profile there. it's non-smooth.
Mm-hmm.
Yeah.
Okay. And did you analyze the influence of changes of parameters at macro scale on the results and changing of parameters of micro scale on the general results?
This should have the influence, but we haven't done that because the input of our simulation is the geometry of the wheel and the geometry of the rail. When that is decided, then the geometry of the contact patch is determined.
Mm-hmm. So you calculated for particular geometries of
yes.
wheel and rail.
That's true.
Okay.
I have just a point for discussion for the community. I'm just curious. I've explored similar ideas, and for rail where there is a lot of plasticity involved as well.
A lot of what?
Plasticity.
Plasticity.
Yes. How do this concept of asperity contact and plasticity interact with each other?
So for the asperity contact, the force curve I use, that includes the plasticity of material.
Okay. But you think that as a evolution, the asperities will still be there, or they will be rolled away by high plasticity?
I think it's already included in that.
Okay, maybe we will discuss as we have two more presentations, and maybe we discuss the others one. So about sanding, influence of adhesion in sanding phenomena. Maybe you will explain us your main not topic, but idea. The sand change the distribution of normal force, improve the friction coefficient around, which leads to adhesion enhancement. Please support this idea, main idea.
Okay, because the sand particle between wheel and rail, so the distance between wheel and rail will change, and the normal force, normal pressure distribution will change because of the distance change, and and the sand friction coefficient between sand and steel is different between different with rail and rail. The traction boundary will change, and this causes the adhesion area increase, and the adhesion enhancement.
Okay, and did maybe questions? Yep, please your comment.
A well-known problem with sanding is the damage that occurs to the wheel and the rail, which suggests that plastic flow is very important. Is that included in your model?
You mean sand crust?
The hard sand particles cause local plastic deformation of the wheel and the rail surface. And maybe the improvement in traction is due to the sand particle as a third body between the two, sitting in a dip. So a bit like your model, where the sand is becoming an extra big asperity.
Now we just... sorry.
Okay.
We can discuss.
This is the time to finish our session, but I think that we will continue discussion during the break, and I thank all the participants for participation and fruitful discussion in our session, Contact Mechanics. Thank you very much. Thank you very much, our presenters.